Right, let's get this going. So, hey everyone, thanks for coming along tonight. First things first, quick introduction from me before we get going. My name's Steve Collins. I've been programming in one form or another since the early 80s, which makes me incredibly old. I started with the ZX Spectrum, and professionally I've been doing this since the early 90s, starting with VB3 right the way through to now using .NET 5. I've got quite a common name, so I go by the alias of Steve Talks Code for both my blog and my Twitter handle. I've got a lot to pack in the next hour, so if you've got any questions, please pop them in chat window and I'll try and answer them as best I can afterwards. So with the introductions out the way, let's take a deep dive into dependency injection. So before we get going, I've had to make a few assumptions about what you may or may not already know about dependency injection in .NET Core. First is that most of you are familiar with using a host builder of one flavor or another to go and create the container. Now, whilst you can also go and create the container directly from the service collection without the host builder, I'm not going to focus on that too much in this talk. The next assumption is that you're familiar with using a startup class to register your services via the configure services method. And then you point the host builder to your startup class via the use startup. So as you can see here, we're using the default host builder to set up the web application using the more specific web host builder. Next, there's various types of dependency injection supported by many of the IOC containers out there. But for now, you just need to be aware that out of the box, the .NET Core container only supports constructor injection. Now, when I say .NET Core throughout the rest of this talk, I'm also including .NET 5 and beyond in that term. But I will be calling out some specifics about .NET 5 and C#9 a bit later. If you're using ASP.NET Core, you do get to take advantage of one of the other types of injection, which is method parameter injection. As you can see here, all you need to do is add the from services attribute to the parameters you want injected from the container. This means that if you have many actions on your controller and that they have different dependencies, you can avoid injecting all of them into the constructor every time it gets fired up. This means that your controllers and your action methods are much more aligned with the single responsibility principle from Solid, because you're only having to inject just what's needed into the action, rather than maybe 20 different dependencies that cover lots of different things into your controller. Now, usually, if you want to go beyond the basic out-the-box experience of the Microsoft container, you need to go and look at using other containers, and I'll cover that shortly. Now, I touched on that there were other injection types, so I said about constructor injection and method property injections, but there's other types out there as well. These include property injection, and this is where a class is parameterless constructor, so you can't inject the dependencies via constructor injection. You have to go and new it up and then go and set the properties one by one. Once you've done that, you've usually got a method, something like initialize or create, something like that, that then says that the object is ready to use. Next, we have named or key-based injection. This is where you identify a dependency instead of sort of by the type in the constructor. You say you identify it by a string or an enum value or some kind of constant. Last on the list, we have automated service registration by convention, which is a bit of a mouthful. But in essence, what it's doing is the container or some tool around the container scans the assembly and pulls out classes and interfaces to register based on set conventions or rules that you specify when you set up that tool. The good news is that I'll be showing you some workarounds so that you can implement these without having to necessarily go and use one of the other IoT containers. But why are those other styles of injections not supported? Well, the Microsoft container is what's known as a conforming container. And it's a term that sort of Mark Seaman has coined, but it's kind of a fancy way of saying that out the box, it just supports the lowest common denominator of functionality that Microsoft needed to support to get a DI container going when they started working on .NET Core. But it also acts as an abstraction so that other containers can hook into it via a common interface. So you're probably aware that there are a number of other container frameworks out there that can be used with .NET. So in this slide, I show the ones that are listed on the Microsoft Docs website as having been adapted or extended to work with the iService provider interface. Now, the downside is that if you want to use functionality that's not directly supported by the iService provider implementation on the container, You then end up having to manage both your interactions with both the main iService provider and the custom IOC to the side. So you need to know who and how is resolving your dependencies. And you could get in a bit of a pickle if you think one's doing it and then the other's doing it. Historically, if you're using .NET Core 2, you would usually wire one of these containers in the configure services method in the startup class and return an instance of iService provider. So in the example here, I'm using AutoFact to register an AutoFact module and return a new AutoFact container. But this all changed when we moved from .NET Core 2 to Core 3. But before I come on to that, let's look at your typical service registrations. So in this snippet here, we have code that you're likely to be familiar with. In this example, we're just registering some classes with a service collection and giving them different lifetimes. As we've already covered, in most applications, you'll be using the host builder that initializes the service collection with some default services. Once it's done that, it'll call your startup class's configure services method to go and add the registrations you've specified as shown here. After that, it will then call the build service provider method on the service collection to create the container instance based on the service registrations. Once built, the container is then used to resolve the instances of services whenever they're required. Now, on the previous slide, I said that we're moving from Core 2 to Core 3, or .NET 5 as it is now. We no longer required to return the service provider. In fact, it's now actively discouraged. If you try and return the service provider from configure services, you'll get this Roslyn analyzer warning. The reason for this is that since Core 3, the way the service provider is created by the host builder has changed. What it also means is that whilst in Core 2, there was a small performance boost by implementing the iStartup interface when using the web host builder, this is no longer supported in the generic host model. If you want to use an alternative container, there is a use service provider factory extension method that you can call when setting up the host builder. And that gets your alternative container to resolve instances for you via the Microsoft abstraction. Whilst that will register the custom container, you still need to go and perform any container-specific configuration within the configure container method. Now, you can do this using the configure container extension method on the host builder, but to be honest, it's a bit of a pain there. So it's a lot easier to do it using it inside your startup class, like you've done with your configure services and configure method as well. So for example, we have AutoFact here. Whichever way you choose to do this, you receive a builder instance that's specific to the third-party container and allows you to use the container's own registration methods. For example, AutoFact can provide a container builder where you can register modules. It's important, though, to know that as the container is built by the host builder, you can't actually access the created container until you get to that configure method, where you access it via the application services property. So having covered how the container gets built, let's give some consideration to the lifetimes of the object instances you want the container to create for you. Now, I'm sure that this is familiar territory, but I've included it to make sure everyone's up to the same level of understanding before we delve any deeper. Firstly, we have singletons, which are created only once and live for the duration of the container lifetime. Then we've got transients, which are our fair weather friends that come and go as and when needed and created on the fly when you want them. Last but not least, we have scope lifetimes, which stand between the other two, and I'll go into a bit more detail a little bit later on. The thing to consider with these different lifetimes is that some of them play well with each other, and others really should be kept well apart. So let's break it down. Starting with the shortest lived of the lifetimes, the transient can accept objects created with any of the three lifetimes. Moving up through the lifetimes, next we have scope lifetimes. They're a bit longer lived, so you shouldn't really inject a transient lifetime into them because that's much shorter than the scope lifetime. Lastly, we have singletons, and again, you shouldn't inject transients or scopes into those. Now, I'll try to choose my words carefully when describing these. I'm not saying you mustn't, I'm just saying you shouldn't, because there's a general misconception that it's not actually possible to inject incompatible lifetimes into each other, but that's not strictly true. I can't speak for the other containers, but the Microsoft container won't actually stop you. If you have a singleton and its constructor requires an instance of something that's been registered with a shorter lifetime, the container will happily give you that instance. The problem is the instance you will get will have its lifetime promoted up to be the same as the receiving instance. In other words, a transient instance will be locked into a singleton and not released until the singleton is disposed of. And that doesn't happen until the container is done and dusted. This is known as a captured dependency, where the transient or scoped instance, like the insect in amber shown here, is imprisoned in the outer shell, which in our case is the singleton. Now you may be going, hang on, pause, what are you saying? I've got an exception when I've done that before. That can occur, but by default, it only happens when your ASP.NET Core environment is set to the development constant. Reason is that there's some hidden magic going on that lies in the host builder that checks for that. However, you can explicitly turn on this behavior by setting on the optional validate scopes parameter to true when creating the service provider. But this does have a performance hit at startup because it's constantly rechecking itself. So the general guidance is not to do it in production, and that's why Microsoft have sort of baked in this sort of guardrail that says it's only on by default in debug mode. Whilst I haven't got time to cover it here today, there's also a validate on build method. That will try and identify registration problems where you've got a dependency on something that hasn't been registered. It's fairly limited in the programs it can identify, but especially if you do any of the fancy registration types that I'll come on to in a little bit. So moving on, given that singletons live a long time and can be dangerous when mixing with other lifetimes, let's consider why we would use singletons in the typical use cases. Given singletons can be accessed anywhere within an application because it's all shared, things get tricky if your application uses multiple threads. Therefore, singletons should really ideally be stateless, so you avoid the threading complications. But sometimes you may well have to have some sort of state that you need to share. These might be pooled resources, in-memory queues, or some other type where you're in control of a limited resource that multiple things are dependent upon. Factory classes I'll talk about later, but typically these are created once, and then their methods are called to create shorter-lived instances of some other dependency on an ad hoc basis when they're required. You may have come across an ambient singleton, which hides the complexity of accessing shorter-lived objects. Now, the thing you may be familiar with is the HTTP context accessor in ASP.NET Core, and that uses async local storage under the bonnet to avoid the capture dependency problem. The last of the cases shown here is immutable state, where you don't want to have to recreate a resource object over and over again when you know that the data that it holds won't change while the application's running. So, for example, you may have some lookup data that you read once from a slow repository, such as a database, a file, or some kind of network service. If you really must have state, give some thought to letting .NET do some of the heavy lifting for you. If you've got collections, consider using the concurrent collections namespace where the thread safety stuff has been already done for you effectively. So you don't need to worry about a lot of that stuff. There's various methods where you can sort of say, try and add this, try and remove this, and so on. For read-only properties, make the underlying field read-only, so that if someone comes along later and tries to make it read-write, at least you've tried to put some guardrails to make them think, well, this is read-only now. Do I really need to make this read-write? If those properties really must be read-write, you may want to consider using a thread lock. Now, this is a contentious issue, but bear with me on this. So in this slide, we can see that we're ensuring that all the property access is managed by a thread lock. That way, we can ensure that the values only change by one single thread at any one particular time. Now, as you're probably aware, the problem with this approach is that by serializing the access to the property, you'll get a major performance hit, especially if you're, say, on a web server, where you're forcing all threads and all accesses to that property down a one-at-a-time alleyway. And you end up with threads queuing up. Potentially worse, you may even end up with thread deadlocks. So if you find yourself doing this, you may want to take a step back and think, should this be a singleton? If it is a singleton, is there something I can do with using one of the out-the-box things to manage my thread safety? Because especially on a web server, if you're using thread locks, that's probably an alarm bell should be starting to ring. Now, I don't have a panacea for this. I'm just waving my flag and giving you a warning that if you're having to do that, you may have problems with your design. The last thing to consider is maybe the impact of having disposables in a singleton. The problem here is that if you call the dispose method on a singleton, or rather, if you've got a dispose method on a singleton and a consumer calls it, let me try and get that right, everything else has lost access to the disposed resources, which can cause an object disposed exception to be raised elsewhere in the application. However, you still do need to make the dispose method available for the container to clean up after itself once it's done with the resources and it's tearing down the container. So to get around this, you may want to consider abstracting the class away with an interface that exposes all the members except the dispose method. That way, as the service type is the interface and not the concrete class, when the instance is served up from the container, you've put some guardrails in place that make it difficult for the consumer to accidentally call dispose. Now, if someone's being particularly, I can't think of the right word, but obtuse, that doesn't stop the caller from casting the instance back into the concrete type and calling it dispose. But it's their foot, and if they want to shoot themselves in it, so be it. For transients, there's not really a lot to say, other than be careful about what you're doing a lot of work in the constructor, as you don't have control necessarily of when those instances are going to be created because it's been done by the container. This could have a major performance hit on your application if they are doing something like getting data from a database each time they're created, rather than explicitly through a method call. Moving on to scope lifetimes, these need to be approached with caution and handled with care. In fact, I've seen various blog posts and tweets where people have said that they have banned their use on their projects. I think that's a little bit drastic, to be honest, but I understand the reticence, as they can come back and bite you when you least expect it if used incorrectly, or not necessarily incorrectly, used naively without understanding the full implications. So hopefully I can clear up some of the pain points. We've already covered how scoped instances can be used with other lifetimes, but what exactly is a scope lifetime? The commonly quoted answer is that they're created by ASP.NET Core for an HTTP request response lifetime, but that's not really the whole story. Whilst it is a common use case, a scope is not tied to ASP. You can go and create your own scopes. That still doesn't answer what a scope is. In my mind, a scope is really there to ensure that objects are only created once within a single unit of work. So say you have several classes that are all considered to be within a single unit of work. These classes interact with each other and all depend on receiving, say, an iWidget instance in their constructor, which is created by the container. Therefore, you may want to make sure that they all receive the same instance of the same widget from the container. So in that respect, the scope lifetime is quite like a singleton in that it's a shared instance that can be consumed by several classes with the knowledge that they'll get the same instance and can interact with it. However, outside that unit of work boundary, you would expect to get a different instance. So in that way, it's a bit like a transient in that every time you spin up a new unit of work, you want a new instance. So to come back to the common use case of a web request, if, say, Bill and Ted each make a web request, those request response pipelines are individual units of work. And you would therefore expect the scoped instance to just live within that unit of work. And you wouldn't want any cross-population between Bill's web call and Ted's web call, especially if there's some state in there, thinking GDPR and stuff like that. So you need to be very careful. And that's where the scope lifetime comes into its own. However, as I talked about earlier, it is possible to accidentally promote a scope dependency lifetime up to a singleton if it gets injected into a singleton's constructor. Away from the web, you might be writing a Xamarin or a console app, and you may want to manually create a scope yourself. This is done by calling the create scope method on the iService provider instance. This gives you back an iService scope. There's a single property of service provider, which is another instance of iService provider again. But this time you've created a boundary that will serve up scope services. That's all a bit of a mouthful to explain. So maybe looking at how ASP.NET Core does it will provide some more clarity. So in ASP.NET Core, the creation of scopes is taken care of you when you start the request response lifetime. The server will create a load of service features. I think there's about 20 or 30 that get spun up. But the one that we're interested in is the request service feature. As I described just now, The scope factory is used to create the scope as highlighted here. That scope is then used to create a scope service provider, which is then accessed from the HTTP context request services property. Now, as someone writing an ASP.NET controller, all of this is hidden away from you, and quite frankly, you don't really care about how this is all going on. All you need to care about is specifying your dependency in the constructor or action method of your controller or endpoint. However, there is one area of ASP.NET Core where it is worth knowing what is going on under the hood, and that's middleware. When we talk about middleware, we think about usually intercepting and handling HTTP requests and responses. Now, because of this, you might assume that middleware is a scope registration, but that's not strictly true, as there are two different ways of writing middleware. The one that most people are familiar with is convention-based middleware, as shown here. With this type of middleware, you accept a request delegate in the constructor and then call it from within the invoke async method to move on to the next middleware in the pipeline. Either before or after the delegate call is where you do your own work. In some cases, you might be writing terminating middleware, where you generate the response and don't call the delegate unless you cannot handle the request yourself. This is something like the static file middleware, where it sort of says, I'll go and find this file in the file system, and if I can't find it, I'll pass it down the chain. If you have dependencies other than HTTP context, you can add those as parameters to the invoke async method, and they magically appear when the method is called by the pipeline. But how does this all happen? When you register middleware, it's done in the configure method of the startup class. At this point, the container is already baked, so you're not actually adding the middleware to the container. Instead, what you're doing is inserting a delegate into the invoke async method that will be doing the actual work in the pipeline. To do that, a single instance of the middleware class is created by the use middleware method. When that single instance is created, any dependencies are resolved from the root container. Now, as you saw earlier, if the constructor is only called once, when you inject a transient or scope dependency into the singleton constructor, it'll effectively become a captured dependency. And this is where you need to be aware of what your dependencies are and what lifetimes they've been registered as. What you also need to bear in mind is that the pipeline is created before the first request is received. So you won't be able to access anything related to HTTP context in the constructor, as it doesn't exist at the point that the instance is created as part of the use middleware pipeline. If you do have an HTTP context in your constructor, then you're likely to get an invalid operation exception thrown, as it can't be resolved at that point because it just doesn't exist. Other scope dependencies that are not part of the pipeline may resolve, but as I said earlier, they become captured dependencies. So how does the request that is scoped get dealt with? Well, as the request moves through each layer of middleware in the pipeline, the invoke async method gets called through the delegate chain, not through some interface or abstract contract. To do this, when the middleware is added to the pipeline, the request delegate is created. The delegate acts as a wrapper over the invoke async method. So as you can see, the request delegate is passed a parameter in the middleware constructor to enable the request to be passed down to the next one in the pipeline. You are free to add any scoped or transient dependencies as parameters to the invoke async method if you need to. You might need them to do some work, and typically it might be something like doing some logging or something like that. Now, in the previous example, I demonstrated how dependency injections works with convention-based middleware. What is less well known, and I only found out about this a few months ago, is that there's an interface that got introduced with Core 2 called iMiddleware. And what this does is it allows you to write middleware in a similar way as how you write your controllers and POCOs that get registered with the container. Now, the problem with the convention-based way of middleware is that it's a bit clunky and lays a few bear traps for you if you unwittingly declare transients or scopes as constructor parameters. What iMiddleware interface allows you to do, it effectively turns the convention-based approach that I've just described on its head. So this time, the invoke async method has a fixed signature defined by the iMiddleware interface. Whilst we still get the HTTP context passed into it, this time the request delegate is passed in via the method and not the constructor. So given that the method has a fixed signature, we have to go back to the constructor to inject our other dependencies. What is different this time, though, is that the middleware instance is constructed by the DI container and not through some hidden magic using reflection behind the scenes. So unlike convention-based middleware, we do need to remember to go and register our middleware with the container in configure services. When we call the use middleware method to register the method goes and checks our middleware type and see if it implements the I middleware interface. If it doesn't, it assumes that it's convention-based middleware and carries on as we've just described. But if it does, it gets an implementation of the I middleware factory from the DI container, which in turn calls the DI container to get instances of the middleware that we've registered. Now that seems like an unnecessary extra hop to go via. Why go via a factory when the container already knows? But why don't we just go to the container? Well, when you read through the notes on GitHub by people like David Fowler, the reason it's there is so that it adds a layer of abstraction so that other containers such as AutoFac can also register their factory implementations. So if you've got any fancy registration going on with one of those, it can still build it into the chain rather than have everything having to go via the iService provider. So going down this route, writing middleware becomes a lot more natural as you write it in the same way as you would with other .NET classes, such as your controllers and POCOs, and you register them in the same way with the DI container. If you're finding it interesting in finding out a bit more about convention versus factory-based middleware and how they work with dependency injection, I have a blog post that goes into more detailed comparison and describes how the two interact differently with the underlying use method on the application build class, which is the thing that actually does the building of the pipeline for you. So earlier I mentioned to be careful with disposables, but now I want to dig into a bit deeper with it and look at some edge cases. If you remember, when I was talking about singletons, I said that you should hide the dispose method for consumers as the container will take care of it. The last bit of that statement is true in most cases. But as you can see here, there are a couple of extension methods where you create the instances yourself, and the container will not dispose of these for you. If you do create the instance of the disposable class in this way, there's a bit of a problem. Namely, there's no obvious re-entry point back into configure services method or the startup class itself to get a reference to the instance to then make it disposed. So why would you take this approach? The reason you may be creating an object in startup is to pass some arguments to the constructor where the parameters cannot be created by the container. If that is the case, maybe you should consider writing a factory. But if you really must do this, you do have a get out of jail card. Behind the scenes, there's an interface that is automatically registered by the host called iHost application lifetime. This can be injected into the configure method by adding it to the parameter list. Here you can register a handler for the application shutdown, which is past the object that you want to dispose of. Now that's fine if you've just got the one object, but it does get a bit messy if you've got lots of them because you have to go and extend that method signature with all of them. If you really must go down that approach and you've got lots of them, firstly, you may want to think about your design and maybe using factories, stuff like that. But worst case scenario, what I would say is maybe you should create a composite class that then holds all those disposable items and has a dispose method itself. And when you call dispose on that class, it goes and disposes all the others for you. So it simplifies your code a bit. Coming back to hiding the dispose method, if you can't change the class because you just don't own the source code and it doesn't already have an abstraction that hides the dispose, you may want to consider using one of the gang of the 4 patterns such as facade, adapter, bridge, or proxy. These are all variations of the same kind of theme of basically creating a wrapper class to handle the creation and disposal of the class instance for you. The last point I want to make is a rare one and a code smell. If you have a class that's a control freak and insists on disposing instances passed into it, then instead of getting the container to create those instances for you, again, you may want to use a factory, and the instance that the factory creates can then be disposed by that control freak. Next, we have some gotchas that can come up when registering or consuming services from the container. Consider what happens when the same service type gets registered multiple times against multiple implementations. You may well be doing this deliberately because you want to have several implementations that you want to iterate through. These might be a set of validation rules or a collection of processing types that form some kind of enrichment pipeline that you chain together using, say, the visitor pattern. But it can happen by accident. For example, you may have a source code merge that's gone wrong, so the same line appears twice in your code, so you've registered something twice. You may have some extension methods registering a different implementation to the one you're registering without you knowing about it, especially if you're using third parties and some of the common classes. Whatever the reason, there can be unintended consequences because of the way the container works. Namely, it works on a last in wins principle. So if you call an extension method after your registration, it'll be the extension method's implementation that'll be the one that gets resolved by the container. So you need to give some thought as the order in which you chain all these things together when you write your configure services method. Of course, if you're writing an extension method, especially if you're publishing it to a wider audience via NuGet, the onus is on you to play nicely. As we know, there needs to be care around lifetimes, and things get messy if there are multiple registrations with different lifetimes. So you may think you've registered a singleton in your configure services, and then someone comes along with an extension method and then registers a transient or a scoped using the same thing. And that last in win principle means that lifetime is different to what you were expecting. Now, it may be that, as I mentioned just now, you deliberately want multiple implementations. But if we do want to avoid accidentally registering multiple services, then there are two out-of-the-box ways to get around this. The first is to use the triad methods, where the first registration is kept and subsequent registrations are ignored, a bit like the triad on the iDictionary, for example. So we flip from a last in wins to a first in wins, in that if something already exists, it just says, I'm not going to register you, go away. The second approach is to use the try enumerable methods, where both the service type and the implementation type are taken into account. So in the examples here, we have the triad singleton, which will result in just one registration, even though it's been called 6 times. But the triad enumerable will result in 3 registrations, as the implementation type is also taken into account. So that's the gotchas net done. Now let's look at some helpful hints and tricks, and just stop for a quick glass of water. Right. Flipping what we've just talked about on its head, you may be deliberately registering multiple implementations that the caller needs to iterate over. As I said, it might be some validation rules or a visitor pattern, something like that. If you do plan to do this, the consuming class needs to know that there are multiple registrations. Otherwise, if it just asks for one, it'll get the last or first, depending on whether you use triad or not. To do this, the consumer needs to explicitly request an IEnumerable of the service in its constructor parameter list. That way, it will get the whole list of all the different registrations come through. If the order of the enumerable is important, there needs to be a way of differentiating the different instances. Without that, the consumer will have to rely on the order that the registrations were performed in back in configure services or in extension methods that get called. There's lots of ways of handling that. One is to create a comparer that implements the iComparable interface for your service type. That can be used with an order by link when they're received in the enumerable. You could create a dedicated class that implements IEnumerable interface, and the caller requests that. But for that to work, you would need to inject an IEnumerable of the service type and then have some kind of logic in there that works out the ordering. Not hard, but a bit clunky. Lastly, you could just do it inside a Lambda expression inside the container. Going the other way around, you may have a single class that has multiple interfaces, especially if you've gone down the interface segregation principle route from Solid. If you register the type with each interface individually, each registration creates its own distinct instance. Really, especially if you've got a singleton or a scoped, you want to get that same instance back. So if you want to get access to the same instance through different interfaces, what you need to do is first register the instance by its class type, and then use Lambda expressions using the getRequiredService method to resolve the instance from the iService provider from the container. So effectively, you're piggybacking on saying, get me the original class, and now I will then cast it to the appropriate interface when you ask for that interface via the container. In some cases, you may want to aggregate the interfaces together into a composite interface as shown here. This may be a benefit if you don't want consumers to be able to request the concrete implementation directly, because remember, we've just sort of registered the concrete in there. So unless it's internal or private, then it's available for the world to use. You're not forcing people to get it via the interfaces. That can be a problem if you think back to what I was saying about hiding the disposable issue. In the example here, I've registered my implementation using an aggregated interface rather than the disposable concrete class. I've then registered the same singleton instance against the individual interfaces to retrieve the same instance by calling back into the container to get the aggregate instance. Next, we have open generics, where you define the type parameter on the class type. Now, the place you may be familiar with this from a DI perspective is the generic iLogger T interface, where you may be using it in your controller constructors to get an iLogger instance for the type of your controller. Similarly, you may be familiar with the iOptions interface, which gets registered when you use the configure method to bind configuration to objects. If you want to register your own open generic type, the C# syntax doesn't really lend itself to referencing open generics with the generic declaration. The language just can't cope with it. So instead, we have to use a non-generic registration method where we use the type of keyword to get the service and implementation types without giving a closing parameter, type parameter. In the case shown here, the iDoSomething generic interface and the doSomething generic class are shown with the angle brackets, but you'll notice that there's no closing type, as this will be supplied by the consumer when it does its constructor parameters. Behind the scenes, the container makes use of the makeGenericType method on the type class to create the closed generic type. For example, the doSomething generic of strings. It then uses that type with a bit of reflection magic to create create the closed generic type to return to the caller. If you have not moved to .NET 5 yet, there is a gotcha. You will hit a problem if your type definition includes a constraint on the generic type, such as limiting it to being a class or limiting it to being a particular interface or inheriting from some base class. The problem is that the makeGenericType was thrown an argument exception. Luckily, that's where Jimmy Bogard of Automapper and Mediator fame has come to the rescue. He did a pull request that added a try-catch block around the makeGenericType that swallows the argument exception. This now allows the constrained generics to be resolved in .NET 5, which is great, except it took 4 years for that pull request to be accepted by Microsoft. Now, if you read Jimmy's blog, you get to understand why there's been very little change in the Microsoft container since the first version of .NET Core. In short, you must ensure that all the other container technologies that implement iService Provider, so the likes of AutoFac and Inject and all those, you have to make sure that they don't break. So to do that, you have to write a whole load of unit tests for all those different containers, not just the Microsoft container, to A, show that your change fixes something or brings something new to the container, and B, that it's not going to break anyone else. Next, I want to talk about a couple of so-called Gang of Four design patterns that are relevant in the DI container world. The first is the factory pattern, which I've mentioned several times in passing. You're probably fed up with me talking about factories because it's my little hobby horse. Now, you may be thinking, Steve, surely the whole point of the container is to be a factory. So why do I need to write a factory class? And hopefully some of the examples I've given. Sometimes you just need to give the DI container a bit of a helping hand. For example, you may have a class that some of the constructor parameters just aren't known until runtime, as they may be captured from user input. Think of something where you capture a name as part of the user input, and that then goes on to be constructed to go and construct something else. Now, you can kind of do some really hacky workaround with the async local, but that's really nasty, so you just don't want to go down that route. You may have another situation, and I've touched on before, where you've got something that's a bit of a resource hog. So you want to spin it up and get rid of it quickly because you want to dispose of the resources that it's using. So again, you use a factory to go and create it, use it, and then get rid of it. Lastly, at the start of the talk, I mentioned that the Microsoft container doesn't support property injection. But by using a factory, we can effectively simulate property injection by getting the container to instantiate the class and then set the property values for it before handing it back to the client. These are just a few cases where the factory pattern really comes into its own. So as a quick and very contrived example, we have a class here that we will register as a singleton. Next, we're going to create a class that consumes the singleton, but also requires a name parameter in the constructor. Now, given that the name parameter cannot be known by the container, as it's provided by, say, our API controller, for example, we can't add it to the configure services. Now, you may notice here I've used an immutable class here, but with C#9, I could have used a record type. Now we'll go and create a factory class. First, we will take the singleton and cache it in a field, as shown in the blue highlighted constructor. We then have a creation method that will go and new up our short-lived thing, and then cache the singleton. And then a value is passed in to the name parameter that we have on the factory method. Next, we add the factory to the configure services as a singleton. Excuse me. And finally, we have our controller that takes the factory into constructor. Later in the get action, it then calls the make method to go and create a new instance of the short-lived thing. Now, I know that's a very contrived example, but it gives you a flavor of where the factory method can help you bridge the gap between the knowns from the container and the unknowns that are coming in from elsewhere. And also, sorry about the small font in there, but there was a lot to pack into the one slide. So to summarize factories, usually you'll register a factory as a singleton, as most of the time it's stateless. The variations are parameters in the create method. As it is a singleton, the only other dependencies should be injected into it are other singletons. If you need transients or scope dependencies, you can take the iService provider itself as a constructor parameter, but proceed with caution. Direct use of the iService provider is considered a version of the service locator anti-pattern. Now, the reason it's an anti-pattern is that it's tight coupling to the container interfaces, which in most cases you don't really want to do. You want your classes to be oblivious to the container. However, the factory pattern classes fall into a group that I refer to as servicing classes. These are plugging the gaps in the container functionality and are effectively an extension to the container rather than being part of your main application. You've usually got them in a library that sort of sits quite near the container. So with this in mind, I think that as long as the factory classes are seen as that context, and you don't go referencing iService provider wholesale throughout your application, I'm fairly relaxed about doing this, as it's be about pragmatic rather than dogmatic. If you're worried about the factory classes exposing the anti-pattern and the coupling, you can always create an interface and make the class private inside your startup class. That way the container can construct them, but callers can only access the registered methods. It can't go and get an instance that then has the iService provider in. A variation of the factory pattern is the builder pattern, where rather than prescribing which dependencies are needed up front and creating the instance immediately, the builder is much more flexible. The way I compare the two patterns is to think of the two as ways of ordering drinks in a fast food restaurant. The factory is like asking a person to serve you a cola using a standardized dispenser with a fixed set of options that make standardized drinks. You know what you're going to get. With the builder, it's a bit more like the modern dispensers that you sometimes see, where you can sort of say, okay, I've got a base cola, but I want to add a dash of lime and a dash of vanilla and some cherry flavoring. And it's up to you how you gradually compose up that customized value until you've got your finished drink. So with the builder, we start off much like the factory by registering it with the container. However, this time we register as a transient, as you're going to be mutating state as you go along. So once the container has served it up to you, you then start manipulating it to eventually get to a method where you can now say, I'm ready, now go and create it for me. The consuming classes take the builder as a constructor parameter and then start using the methods and properties to do that building. Typically, the resulting instance will be immutable. The last thing to mention is that, like the factory though, if the instance you created out the builder is disposable, the caller will be responsible for calling the dispose method on it, not the container. Now, so far, we've assumed that the factory or builder classes will be using the new keyword to instantiate the class instance. But wouldn't it be good if we could take advantage of the container to do the creation for us? Now, in the earlier slides, I said that the problem was working out how to populate the parameters the container doesn't know about. Luckily, this is where the activator utilities class comes in handy. There are 4 methods, effectively 2 methods with generic overloads. The get service or create service will try and get the container to create the instance for you. But if the type is not registered, it will do it via reflection. The other method is one that of interest to us as writers of factory or builders, is the create instance method. What this does, it takes an instance of iService provider to get an inroad into the container, and then it takes an array of objects. It then does the work of trying to match the constructors on the requested type to what's been supplied in the array and filling in the gaps. So it's a bit of a sort of shuffle of mixing them around until something fits. Now, the downside to that is because it's doing that shuffling around, you may take a bit of a performance hit if you've got lots of parameters coming into the constructor. So maybe you want to use it with care, and you might want to just new it up explicitly. But where this is useful for our factory or builder is instead of explicitly declaring all those types, especially if there's a lot of them, it does simplify your code a bit. So it's 10:02, so I'm coming into the final section now. Lastly, I want to talk about plugging in some of the gaps of functionality that the Microsoft container is missing. I mentioned earlier that property injection is not supported out of the box by the Microsoft container. And as we've just seen, you can get around that with the factory or builder pattern to go and create your instances for you. Another place where this can be useful is if you need to create instances of struct value types, where some of the properties come from the container. The problem here is that you simply cannot register value types with the Microsoft DI container as it's not supported. So you need to get all the dependencies and instantiate the value type itself. So here you see I'm attempting to add a struct type registration to the generic add transient. And here's the Roslyn error to say that's a no can do. So you may go, haha, it's because I'm using the generic registration. I'll try the non-generic version. And that's great. You don't get a compile error, but all you've done is you've kicked the can down the road to be a runtime error, which is even worse for you. So how do we get around this? So if you really must have a struct type, and I do question whether it's even worth it, but you can create a factory or builder that takes parameters to go and need to populate some of the values of your struct type, and then you can go and do the rest of it again with a factory. But talking about immutable types, that leads us to the new C#9 record types. Now, I'm a big fan of these and been making a lot of use of them in the projects I've been writing over the past couple of months. For those of you not familiar with these, they're reference types like classes, but they behave like value types when it comes to things like equality checking. They also offer a simplified syntax for immutability. If you want to find out more about them, I like the on.net show video that I've got a link to here. From a DI perspective, as they're reference types, you can register them with a container. However, given that record types mainly for use as sort of immutable entities, it's a bit like we just said about the structs. You may question the point of them, but if it's something where you've got some of the parameters that are in the container, like I said earlier, it does give you that sort of way of sort of mixing and matching stuff that comes from the container and stuff that you're supplying from, say, your API controller. If you're interested in finding out more about using C# records and the factories, I've got a blog post there that I wrote a while ago. Sorry, just need to. Next, we have something that no one really talks about with dependency injection in C#. We nearly always talk about classes and interfaces being registered with the container. But delegates are also a first-class citizen and can be registered as well. Now, in theory, you can register the anonymous delegates from the funct family, but these are hard to distinguish from each other because they're generic. So you've got the funct, funct T1, T2, funct T1, T2, T3, and so on, so on, so on, so on. So instead, we can go back old school, right back to C#1 and use custom delegates. Now, I'll go into details on my blog, but I'll give you a quick example. I really, really hate system date time now property, as it's non-deterministic by its very nature because it's real time, which means that if you've got it inside a class, it makes unit testing stuff really tough. But what we can do is go and create a delegate function that will call the system date time now property on our behalf. The signature of our delegate, in this case, is a function with no input parameters, and it just returns the date time. By creating the delegate, we're creating an abstraction without all the ceremony of having to first go and create an interface of something like iDateTime, and then creating an implementation in the class that wraps the dreadful static property and having to do all that sort of stuff. It makes it a lot more simpler. It also feeds into the single responsibility principle, as the delegate does just one thing. It goes and gets a date time. If you want multiple date-time related functions, you may still want to use an interface and a class. But if those functions don't share any logic, then using single responsibility, you could argue, well, just have lots of different delegates. That way you're not binding half a dozen things together that have no real relationship. If you do try and do this with the funct family, then that way you might hit some pain if you've got lots of signatures that are very similar, because effectively, where it's the generic signature, you're registering lots of times, it can't distinguish them, and you're back to the multiple registration problems that we were talking about earlier. From a unit testing point of view, the delegates are very easy to mock or create your own implementation as they adjust, in this case, functions that return a date time. So from your unit test point of view, you can create a version of an implementation of that delegate that returns a fixed date of 22nd of March, 2021, and use that in your unit tests and use that in your insert statements. Now, you may notice I registered the delegate as a singleton and may be thinking that the date time return will be captured. Surely it's a captured dependency. That's not really the case, because what we're doing is we're capturing the delegate, not the delegate's results. So as you don't actually invoke the delegate until you need it, all it's doing is it's wrapping that call to the delegate. And it's the same principle that I talked about earlier when we were talking about the middleware pipeline. So in this very contrived example, I consume the delegate in the controller constructor and cache it in a field. I then invoke it at the time of the constructor is run and then cache the result in a field. In the get action, I force a 3-second delay. Now, you wouldn't really do this in a web application, but I wanted to prove the point. I then call the delegate again and return a string with both values. Now, as you can see here, the result shows that even though the delegate is a singleton, the invocation was done at 2 separate times, and the result is not generated until invoked. So the first invocation is in the constructor, the second invocation's in the method, and therefore you've got the 3-second difference. A feature that is supported by other containers, such as AutoFac, is being able to specify a dependency to be resolved by the container using a string name or key. It's considered a bit of an anti-pattern, as it comes back to the idea that your application code should not know about the container's mechanics. But what if you could do it without your class having to have knowledge of the container? So this occurred to me a while ago when I had a situation where the type of a mapping algorithm to use was determined at runtime based on a value that was retrieved from a database. And rather than writing a massive hard-coded switch statement that sort of said, if you get this value, then go and ask for one of these, and so on, so on, so on, I wanted to lift that and hoist it up back into the container. So I could just say to the container, I've got this value, go and get me the right mapper. Now, it's a bit long-winded to describe here, so there's a link to my blog post, but to give you an idea of what's involved, I'll have an example. Here we create a common interface with some classes. So we've got a temperature converter that converts from different scales, centigrade and Fahrenheit and Rankine, all into kelvins as well, with absolute zero. We then register them all with the container as their actual types. Now, following on from what I was saying about using delegates, we also have a delegate declared that takes a string, and that's the thing that identifies which one we want, and returns the required implementation of the iKelvin mapper interface. Now, in the code here, I've used a simple switch statement based on character value, but I could have done something more advanced using a dictionary or possibly custom attributes on the implementation types, or maybe even sort of C#8, C#9 pattern matching. There's lots of ways you could approach that. Whichever way you choose to do it, the delegate is the secret sauce that allows us to lift the logic out of the consumer and up into the container. The consumer will use the delegate to pass the string key and get back the correct mapper instance that it needs. In other words, we have something along the lines of an abstract factory pattern. So now we have a consumer class called Gettingchas. There's a method to take a scale as a string and a decimal value that it wants to get converted into kelvins. Now, our class has no knowledge of the container's iService provider, so we've got around the service locator situation. And it has no implementation of how to take a string and get the appropriate implementation. All it needs to know is, I have this delegate, I pass it a string, and I will get a mapper back that I can then invoke with a value to convert that value from whatever I said it was, centigrade, Fahrenheit, Rankine, to kelvins. So that was somewhat contrived and simplified example of using inline switch statements in there. Now, I said that there was lots of ways of doing it. And over the weekend, Frank Quidno now, I'm not quite sure how to pronounce his name, so apologies, Frank, if you're watching. He tweeted me and said he'd written a blog inspired by my blog, where he's taken it a bit further and has implementations that uses dictionaries. He also points out some gotchas about if you're injecting the iService provider to do some delegates, there is a risk of getting closures. So it's definitely worth a read. The decorator is another gang of fault pattern that can be used to extend the functionality of the class by wrapping and then re-implementing all the members, but where necessary, intercepting the incoming parameters and outgoing results to do something else. Now, the most common example of where you're likely to use this is to have a decorator that does some kind of logging. So it logs the input parameters and it logs the result going back out. To do this, we still need the original class to be injected into the decorating class, along with any other dependencies, such as our logger. So in this example code here, we have a class called doSomething that implements the iDoSomething interface. Oh, not sure what happened there. Oh, slides have gone a bit weird. Sorry about that, everyone. Not sure what happened there. So first we register the class as a concrete type and not through its interface. Then we have a decorating class called logging doSomething that takes the registered original class and then also requests an instance of iLogger. It then re-implements the getHello message method, this time the code that intercepts the input and output of doSomething's version and then writes these out to a log. We then go back and register the new logging doSomething against the iDoSomething interface, which is used by the consumers. So the last missing feature from the Microsoft container that is supported by others is registration of services by convention and assembly scanning. Now, I'm not personally a big fan of doing this, as I'm a bit of a control freak and I like to know exactly what is going on. As we saw earlier, it's possible for registrations to stamp all over each other depending on what the order that they're registered. However, if you do have masses of classes to register, it can be a laborious task, and I totally understand why you may be looking for some kind of shortcut. There's several offerings out there, but probably the most well-known is the Scruter, where you can define a set of rules and criteria for registering classes and interfaces. Now, one nice thing about Scruter that's not to do with that sort of scanning is the way it allows you to register decorating classes with a much simpler syntax than that one that I showed in the hand-cranked version that I had a few slides ago. And that just about wraps it up from me. Thank you for coming to the talk. I've had to rattle through it at quite a rate to keep it under the hour. I hope there's a few sort of nuggets in there. And I know Andre sort of said it's been recorded, so you might want to go back and watch it again. If you do want to hear any more of my ramblings, I'm on Twitter quite a bit, and I do have a blog where I've written mainly about dependency injection and configuration. A few honourable mentions. Andrew Log has a brilliant blog that covers all sorts of .NET Core related things and is currently writing the second edition of ASP.NET Core in Action, which is available as an early preview ebook from Manning. The Microsoft Docs pages are well worth a look, especially if you're migrating from Core 2 to Core 3 or .NET 5. And last but no means least, Mark Siemens' blog and book are well worth looking at to get a bigger picture of DI patterns and anti-patterns. If you look on the Manning site, he's got two books in there, and it's this one, the Dependency Injection Principles and Practices, is the one that is more up to date and includes .NET Cores, and that's where he talks about the various, he compares things like autofac and inject and all, and he does a comparison across them all and how they compare with the conforming container of .NET Core. With all that said, and I've just about got my voice still intact, thank you for coming to the talk, and